Today's webinar is titled Improve the Stability of Emulsions with Inline Droplet Size Measurements. My name is Benjamin Smith. I'm the Market Manager for METTLER TOLEDO Particle System Characterization. Today we'll be looking at several types of applications where we would be measuring and improving the stability of emulsions. We'll be looking at emulsions and emulsion formulation in consumer products, microencapsulation, emulsion and de-emulsification in the petroleum industry, and emulsions in the polymerization. The droplet size is critical to improve the stability of emulsions and liquid formulations. And ideally, scientists and engineers can accelerate the understanding of stability, consistency, shelf life, or oil-water separation by measuring the droplet size distribution in real time and detecting moments of coalescence or flocculation. The stability of those emulsions really greatly varies with dilution, heating, or pressure. So offline sampling can alter or destroy an emulsion component, and really is not necessarily the best idea when optimizing or looking to make control decisions during an emulsion formulation. However, inline particle size measurement really speeds up the development. Inline measurements can be used to control surfactants or shear or the raw materials without the need for offline sampling. And METTLER TOLEDO specializes in probe-based instruments which can be used to measure how the particle or how the droplet system changes in real time. And these can be used in the laboratory or throughout scale-up to make real informed, real-time control decisions based on how the droplet behavior occurs in the process or in the pipeline. Here's an example of some PVM images captured in real time in process, typically between 10 and 50% oil and water emulsion or water and oil emulsion. The scale on those images is about 1000 by 800 micron. And you can obviously see with different RPM or different shear, we can track the changes, or PVM can track the changes in those droplet distributions for consistency, repeatability, and a real-time understanding of droplet behavior. This is an example of how the two tools, the FBRM and the PVM, might work together. And this is during an emulsification, an emulsion process, where the particle track instrument on the right provides a chord length distribution to fingerprint the particle or the droplet distributions as the agitation is changed. And you can see different agitation speeds between 20 and 50 hertz and the corresponding droplet distribution. At low agitation speeds, at 20 hertz, we see larger droplets with low numbers. And at higher RPM or higher hertz, we can see smaller droplets and many more number of droplets at the smaller dimension in the chord length in microns. On the left-hand side, we see PVM, which really validates what the FBRM is measuring here, and we can see the droplets as the emulsion process takes place. We can use the two tools together to really target an endpoint and ensure consistency, especially downstream from the emulsion process. Here we see FBRM and particle track data trended over time. So we can create a statistic. For example, the area in red on the distribution graph on the upper left-hand side is basically plotted by calculating the statistic, which is the total number of particles between 0 and 50 microns. And that's basically the integration under the curve in red on the upper left. That is then trended over time on the graph here in the center of your slide. And you can see that the red curve or the red trend presents the number of particles counted between 0 and 50 microns. And that's trended over time. So as the RPM changes, between 20 and 50 hertz, we can see a step change in the number of small droplets less than 50 microns over time. You can also track something like the mean over time, and that's calculated in green, and that's reducing as the droplets get smaller. So these statistics can be used to really troubleshoot or understand how a process changes over time and improve the stability of an emulsion. Now let's look at some examples, beginning with the consumer products industry and how we can improve the stability of emulsion formulation. We'll look at emulsions and consumer products, and specifically in creams and lotions. Between industries, the emulsion unit operations may change. However, a process may look something similar to this slide. Whether we start with an oil and water, or in a monomer, or you are adding active ingredients and surfactants and fragrances to the starting materials, one may begin with two immiscible liquids that are added to a mixing tank, and then some type of homogenization is introduced to the system, whether it's high shear or low shear, or simply a recirculation loop or a static mixer. You're introducing some type of shear which would create an emulsion that typically may lead to a droplet system that would move on to some downstream filling line or some type of downstream process. There could be instability in that process, in the dispersion. There could be coalescence or homogenization in the dispersion phase. And of course, there could be instability or inconsistency downstream. So typically we install the inline particle or droplet measurement tools in the tank or in the pipeline, as you can see here, to measure and track those changes as they occur in real time. This example is from Michael Simpson from Schering-Plough Healthcare Products, which is now Merck Consumer Products. And it was originally presented at the Institute Particle System Characterization Conference in 2002. The title was The Use of FBRM to Monitor Droplet Distributions During Manufacturing of Emulsions. And the specific emulsion that Michael had presented on was sunscreen. The goal was to evaluate the effect of homogenization, emulsifiers, and temperature profiles in a liquid-liquid emulsion. And the concern was the oil phase, which contained one or more sunscreen components, which was dispersed in an emulsion, and droplet system was water phase. The emulsion droplet distribution is affected by the temperature, the method of addition, the order of addition of the different phases or ingredients, the cooling rate, the amount of shear or mechanical work, and the quantity of the emulsifier, as well as the type of the emulsifier. On the right-hand side, we see his installations in the lab on the top, where he had a Y piece with the particle track instrument installed in that Y piece. And then in the plant on the bottom, where there was a large pump and a Y piece with the particle track installed into that adapter. This is an example of his data. We can see at several points in time, he's plotted the particle track measurement, and the x-axis is micrometer from 0.5 to 100 micrometer. The y-axis are the counts per second, and what you can see are the just snapshots at different points in the process. And we can see that as the water is added to the oil, the green distribution shifts to the light blue or turquoise distribution when dispersion, the water and oil is added, with shear. And then The red distribution shifts smaller with neutralization, and then during the milling with static mixer and transfer phase, the distribution shifts to pink. So again, users can identify the distribution which corresponds to the ideal batch endpoint and then use the real-time distributions measured by the particle track relative to that target distribution to ensure consistency and stability downstream. They plotted this experiment, and here you can see a plot over time. The x-axis is the record, or the number of measurements taken over time, and the y-axis are the counts per second, which correspond to different statistics. For example, pink are the number of droplets between 0.5 and 10 micron. Red are the number of droplets between 10 and 30 micron, and light blue are the number of droplets between 30 and 100 microns. We also see white is the temperature. And so during the different phases of this process, we can see what happens when the water is added to the oil. You can see a dramatic increase in the number of small droplets. Then during neutralization, we see an increase in the number of small droplets. But then during the cooling phase, the droplet count in the small region between 0.5 and 10 microns decreases, and the large droplets between 30 and 100 microns increases. So this is obviously what we see when coalescence occurs. There's a drop in the fines, and there's an increase in the large droplets, and that could be a problem. So what they did at Schering-Plough, or now Merck Consumer Healthcare, they extended the mixing and extended the shear for this process and saw the number of fine droplets come back to where they were expected to be, and the large droplets decrease. And the interesting thing about this is that by measuring in real time, the engineers and the scientists could make real-time decisions and control or optimize the process as they saw a change or an upset that was unexpected or unwanted. Just incidentally, the kinetic process of destabilization can take several months if the process was just allowed to sit on the shelf. So many users or many formulators or engineers can actually speed up the process by varying temperature or shear conditions in the laboratory in a beaker. And the particle track instrument can be used to predict and measure what the stability may be over time in an accelerated test of destabilization. And we can do that just as we saw here with ability to track droplet coalescence in real time. In this example, we're looking at the emulsification of a consumer product. And in this case, we start with a complex oil and water system, which has fragrances and flavors and other components added. And we can track how the emulsion takes place. So you can see the x-axis is micrometer, y-axis are the number of droplets over time. And for this case, there's a decrease in the number of droplets in the orange changing to the green distribution. And corresponding to that, we see that statistics change as well. We can track before and after cooling, we see a 43% decrease in the mean, and we see a 290% decrease in the number of small particles or some number of small droplets. We can see in PVM the same type of reduction. Before mixing and after mixing, there's a much smaller droplet distribution. After emulsifier is added, it's even smaller. And then after cooling, we can barely even detect or measure the droplets with imaging. We really need the focused laser measurement to get a repeatable, consistent measurement after the very small microemulsion is created. This process, which was originally measured on a small lab scale, was scaled up from 5 liter to 120 liters. And when that was done, the formulators really used the particle track tools to ensure consistency. The formulators identified a distribution which corresponded to the ideal batch endpoint in real time, and then used the real-time measurements to track relative to the target distribution and ensure that the endpoint was consistent and the distribution was consistent at the endpoint. And you can see on the right, between 5 and 150 liters, the consistent endpoint and the endpoint consistency, as well as the same relatively similar median distribution. The FBRM trended statistics are plotted here. And in this case, we've plotted the number of droplets counted per second between 0.5 and 10 micron. And we're comparing between the 5 liter and the 150 liter batch. And we can see that over time, during this 2-hour batch, we see an increase in the number of droplets and then a change in the number of droplets of these fine droplets over time till we reach a steady state at the endpoint. So the particle track trends really enable the formulators to troubleshoot or measure consistency upon scale up and minimize batch failure and ultimately improve the yield for the batch, especially during tech transfer from a small scale to a plant scale. And in this case, we see that the two batches end at the same point, but they follow different paths. And the question that we pose really is, does the path affect the endpoint stability, even if they end up at the same droplet distribution? And that's really a question that should be understood and can be understood during the development, and especially using our tools to track the stability of the process downstream. Microencapsulation may be performed in the chemical industry or in the pharmaceutical industry or in the agriculture industry or other industries, polymerization and so on. This is an example taken from AAPS journal in 2010, published by the United States Food and Drug Administration, the FDA. This is obviously a pharmaceutical example, but this applies to many other industries, whether it's the chemical industry or consumer product industry and so on. The background really is the same. The effect that product and process variability has on the microparticle is essential for successful development, optimization, and scale-up of an encapsulation process. And the main factors that affect the microencapsulation procedure and the final microparticles are the matrix level, the polymer level, the composition, and the inherent viscosity, the physiochemical properties of the active ingredient, the matrix versus the active ingredient ratio, the nature of the solvent, the level and properties of the stabilizer which is used, and the shear stress or the temperature at which the emulsification process takes place. In this example, a active pharmaceutical ingredient was encapsulated in a polymer matrix, and we can see the materials and methods in the top half of the slide. A polymer forming matrix was used, polylactide glycolide, PLGA, and the model active pharmaceutical ingredient was cyclosporine A, or CYA. And you can see 7 batches were performed in this design of experiment with different polymer weight, drug weight, stabilizers, and so on. What you notice on the bottom half of the slide is that depending on the polymer loading or drug loading or stabilizer loading, there was a different amount the API or the drug which was released. And so obviously we can affect how the microemulsion particles or the microparticles behave during the dissolution or during the release of the active ingredient by affecting the emulsion process. And just as we saw in other examples, the FBRM or the particle track instrument can track how the process changes over time. And on the upper left-hand side, we see one graph from the batch 5, and we can see over time how different statistics track the droplet behavior as the emulsion is formed. And you can see the emulsion formed in the first 20 minutes of this experiment, where the x-axis is time and the y-axis corresponds to the counts per second, and they correspond to different regions. The different colors correspond to different regions of the distribution. For example, the pink curve is the number of droplets between 5 and 36.8 micron. Obviously, you can see the dispersion phase, and then the process reaches a steady state as the matrix polymerizes and the microparticles are formed, reaching the endpoint distribution. On the right-hand side, we see PVM images, droplets throughout the process from 20 minutes to 140 minutes, and you can see the initial polymer or monomer droplet polymerized over time. So FBRM and the particle track instrument is sensitive to the number of microparticles which are forming and tracks the shift in the microparticle chord length distribution as the droplets formed. And a good conclusion basically from the paper was that a good correlation was found between the polymer, the drug, and the surfactant level. PVM helped illustrate the shape and the size of the microparticles, and more importantly, showed the steps of the microparticle ripening during the solvent evaporation phase. And this really could serve as, these measurements can serve as useful parameters to assess the effect of different process variables, especially during the development and the scale up of this process. The next example is de-emulsification and emulsification of petroleum-water system. In the petroleum industry, emulsions are often necessary in the upstream transfer of crude oil and in the downstream separation of the oil and water in the crude oil process. In this example from Energy&Fuels in 2013, Dewey Nguyen from Nalco Chemical, which is an Ecolab company, presents an example where they're investigating heavy oil. Basically, heavy oil encompasses about half of the recoverable oil in the world. However, the viscosity of heavy oil is extremely high, about 10,000 centipoise, making flowability a challenge. And it really needs to be down near about 400 centipoise of apparent viscosity at 25 degrees C. So the group at Nalco is looking to create a metastable emulsion to improve the mobility of the crude oil for a period of time, and then create it in such a way that it can be easily de-emulsified and separated, and the oil and water can be separated. And they do that through the use of surfactants. Now, it should be noted that chemically induced emulsions improve the flow rate. However, they create stable emulsions, which are difficult to break and difficult to separate. So in this paper, they discuss polymeric surfactants such as PVA or polyvinyl alcohol, which can improve the emulsion properties and also be separated. And you can see a diagram of a PVA type surfactant on the right-hand side. In this example, the Nalco engineers were using Canadian crude oil with a specific gravity of 0.989 grams per milliliter at 25 degrees C and an asphaltene resin concentration of between 9.6 and 12.9%. They used 25% deionized water to create the emulsion with the polyvinyl alcohol PVA with a molecular weight of 146 to 186 kilograms per mole, and they use a concentration of 1,000 parts per million, and mixer speed 800 RPM. On the right-hand side, we see distributions, the chord length distributions measured by the particle track in real time in the crude oil. So this is without dilution and measuring directly the droplet distribution in crude oil between 1 minute and 5 minutes. And you can obviously see a reduction in the dimension as the distribution shifts to the left, and an increase in the number of droplets as the shift is upward. Later, we'll zoom in on the large chord length area, about 100 micron, and we can see the reduction in the large droplets as those small droplets are forming during the emulsification process. The inline particle characterization provides feedback to balance the amount of stabilizer agents needed to affect the interfacial tension with the process temperature and shear required to create a metastable emulsion. And in this case, the droplet size and the droplet size distribution really are important emulsion parameters related to the fingerprint of the stability and the viscosity necessary to create this emulsion and to create the metastable emulsion for future separation. Now back to the distribution, we notice that this distribution very much is sensitive to the number of small droplets. And one thing I wanted to do is take a moment to explain how the droplet distribution can be presented. In this case, we have a population of cubes, and there's 2 large cubes, there's 9 medium-sized cubes, and a bunch of small fine cubes. And this data, whenever anyone characterizes any particle or any droplet distribution, it can be presented in several ways. On the left-hand side, we see that droplets, or see that particle system, presented on the upper left as a number distribution, and then as a length-weighted, area-weighted, and volume-weighted distribution as we move to the right and the bottom right. So presenting the data as a number distribution or an unweighted distribution in the upper left allows us to have sensitivity to the fine droplets. And presenting the same exact system, the same exact particle or droplet system in the lower right-hand side allows us to weight the distribution and enhance sensitivity to the coarse or the large droplets or particles in the system. So if we look back at the Nalco data, the unweighted chord length distributions are plotted on the upper half of the slide, and the square weighted chord length distributions are plotted on the lower half of the slide. And it's the exact same data. But just like we saw with those cubes, we can gain sensitivity and enhance the sensitivity to change to the small droplets on the upper half of the slide. And the exact same data, we can enhance the sensitivity to change to the larger droplets on the lower side. So the user and the engineer can identify the distribution which corresponds to the ideal batch endpoint or the ideal conditions, and then track the real-time distribution relative to that ideal target to control the quality of their distribution, their quality of their emulsion, and the stability of the emulsion over time. The metastable emulsion created by Nalco was really important in its ability to improve the transport the flow properties of the oil, but also in its ability to separate downstream, because ultimately they were looking to separate the water and oil. So the scientists track the efficiency of the downstream separation using something called the water drop efficiency. And the water drop efficiency is basically measuring how much water separates from oil in 5 minutes and the percentage which separates in 5 minutes. So, for example, a 60% water drop efficiency for a 75% oil in 25% water matrix means that only 15% of the total water separated from the emulsion. The Nalco group use an optical technique to measure that separation. And on the bar graph on the upper side, we can see the water drop efficiency plotted on the left-hand side, and on the right-hand side, the particle track with FBRM technology measurements, tracking the median over time between those different samples. And so that is on the right. Now, the different samples were captured with either preheating or not preheating, and with different amounts of shear, whether it's handshaking with preheating or not preheating, or 600 RPM or 800 RPM with preheating or not preheating. And we can see the effect on the droplet size and on the downstream separation. Now, the exciting thing is that by measuring the inline droplet distribution, one can predict the downstream stability. So by measuring the droplet distribution in real time in the crude oil, one can develop, in this case, a linear relationship between the droplet dimension and the emulsion stability. So with inline measurements, the scientists could quickly optimize and understand the rheology properties and the emulsion stability, and then make real-time or very fast decisions as they develop the process. The FBRM, the particle track measurements, really take place in a matter of seconds. Within 2-second measurements, we can get a clear understanding of the droplet dimension. And that can really be used to improve and understand stability downstream, whether we're measuring in a pipe or in a vessel during development or manufacturing. In this case, FMC Technologies presents the application of de-emulsification in the petroleum industry. This paper was originally presented by Remco Restra at the International Petroleum Technology Conference in 2012, and the title of the talk was Compact Oil-Water Separation Using the Inline Electrocoalescer and Cyclone Dewaterer. We'll be presenting several of the slides where they focus on how they use the particle track instrument inline in a 4-inch pipeline just downstream of their electrocoalescer. And it looked very similar to the picture on the right-hand side, which was actually from a different location, but a similar style installation. No sampling or dilution is necessary, and the electrocoalescer basically is used to separate or optimize the separation of the water and oil, and this is done with this is done with a technique that's described on the next slide. Okay, the electrocoalescer is a inline device which is applied into the emulsion in the pipeline, and it increases the collisions between the water and the oil droplets using an electric field, which destabilizes the film between the droplets which have collided and increases the probability of coalescence. So as the emulsion passes through the electrocoalescer, within seconds it begins coalescing and larger droplets begin forming. The particle track instrument, the FBRM technology, is installed just downstream of the electrocoalescer and is used to measure the droplet distribution in real time and provide feedback to adjust process conditions. Here's an example of FBRM data, particle track data, presented at two different electric fields between 0 volts or 0 kilovolts per centimeter and 1.1 kilovolt per centimeter. The distribution is plotted as a cumulative distribution where the distribution begins at 0% and moves up to 100%. Before any electrostatic coalescence is applied at 0 kilovolts, the green distribution shows that the distribution, the particles are very small, the droplets are small with a median of about 20 or 30 micron. And then after the electrocoalescer is turned on with 1.1 kilovolts, there's a dramatic change. There's a shift in the droplet distribution. A median moves up to at least 300 or 400 micron, and we can still see a little bit of a bimodal distribution, but the real-time droplet count provides feedback, quantitative feedback of the relative change as a result of the process conditions. In this slide, we're looking in depth at the effect of the water cut on the stability of the emulsion, especially with this electrocoalescer applied. What you see on the graph is the median by the particle track FBRM technology on the y-axis, and the x-axis is the water cut in percent. So as the percentage of water droplets increases, we can see that the green stays constant. So this is basically before any voltage is applied to the system. However, the blue line with voltage applied shows a nice curve where the droplet size increases with the percentage of water present in the emulsion. So higher water cut, the higher the droplet size, and certainly the lower the water cut, the lower the droplet size, and perhaps the more stable the emulsion. In this case, again, we're looking at the effect, the flow rate, and the flow rate is presented on the x-axis. We see the cubic meters per hour flow rate, and on the y-axis we see the particle track data, the FBRM median in micron. And what we see in real time is that we're measuring, again, no change with no kilovolts and no voltage added to the electrocoalescer. However, when voltage is applied, we can see that as the flow rate increases, the droplet size gets smaller. And that's can be inferred because faster flow rates result in a lower residence time in the electrocoalescer. So one can use this to understand, the instability or the stability of the emulsion based on the flow rate through the coalescer, the water cut, and other downstream parameters. And in this case, there are two graphs. Each one is a different percentage water present in the crude oil. So 20% water is light blue, 10% water is orange. And on the x-axis is the amount of kilovolts added to the electrocoalescer. So what we can see is that in this case, with a constant voltage applied, higher water cut results in larger droplets, so that means it would be less stable, and lower water cut is more stable. But also, we can effectively see the effect of varying the electrofield strength on the overall stability of a given emulsion. So obviously, higher voltage results in more coalescence. And here's the pressure drop. So the pressure drop in bars are presented on the x-axis. Again, the y-axis is the median. And what you can see is, let's just look at with voltage applied. You can see that as the pressure drop increases, the droplet size is reduced. And this, makes sense because as the pressure drop occurs and with a higher degree, there's more shear effectively on the creating smaller droplets and more stable droplet emulsion. The next example is emulsion and polymerization. In the chemical industry, the polymerization and the final particle distribution is significantly affected by the initial emulsion droplet size of the monomer. And in this case, presented at the International Process Development Conference in 2003, Eric Kukkonen and Richard Bratz from the University of Illinois, Urbana-Champaign, present the use of both the particle track, FBRM technology, and PVM inline video microscope to measure and track changes in the monomer droplet dispersion in an emulsion process. On the left, we see the setup of a very old school FBRM particle track instrument and the PVM. And you can see it installed in a round bottom vessel on the left-hand side, in which the emulsion takes place. On the right, we see the PVM images taken at different points in the process with different RPM between 100 RPM and 200 RPM at different stages of the process. So we can see different levels of dispersion, different levels of coalescence, which ultimately will affect the final polymer particle size. Here we see the particle track data presented at 3 points in time. And the x-axis on those graphs is micrometer. The y-axis are the number of droplets counted per second. And what we can see is that the particle track distributions provide quantitative information about the droplet dimension and count. And the change in the droplet dimension is affected by agitation. And specifically, what's interesting here is that initially at 10 minutes, at 200 RPM, the droplet is very small. Then the RPM is increased to 100 RPM, decreased to 100 RPM, and the droplet coalescence occurs, the monomer droplet coalescence occurs. And then when the RPM is increased again to 200 RPM, later in the process, the dispersion takes place but does not reach the same level as the initial monomer dispersion. And you can see the lower left-hand side, we see the mean plotted at those 3 points in time. And you can see effectively 120 micron mean at the end point there at 90 minutes. This can also be plotted. We can also look back at the PVM images to understand those three changes in the process. And here we see those PVM images plotted on top of the trended FBRM or particle track data. And what you can see is that by combining the particle track and PVM, we can ensure a rapid understanding of the process and allow us to really target the ideal droplet distribution of the monomer. So we see a plot over time. The x-axis is time. The y-axis corresponds to the number of droplets in pink and the mean droplet dimension in green. So we see the initial dispersion of those monomer droplets, followed by the change in RPM, in the middle of the experiment. And then that's followed by a ramp up back to the same initial RPM. And what's interesting is that you can see how the monomer disperses over time. You can see how it takes quite a long time for the monomer to reach a steady state. And that certainly can be affected by shear, surface chemistry, and other parameters which may be adjusted to achieve that steady state and also achieve the desired dimension and number of droplets over time. Now let's look at conclusions. How are the particle track and PVM instruments used to develop a better understanding of an emulsion process? Typically, they are used inline to understand how the droplet system responds when changing process parameters. For example, one can use the inline data to understand the response when varying temperature, surfactants, or agitation speeds. Optimize. One can use the inline particle track or PVM technology to optimize the process by choosing conditions which ensure consistent endpoints, batch repeatability, and process stability. In this case, we can detect the endpoint of a homogenization by tracking how the droplets change till they reach a steady state. And scale up. We can use the particle track tools and the PVM to scale up a particle or droplet distribution while avoiding batch failure or inconsistencies which may occur due to inconsistencies in the raw materials, the shear, the temperature, or other fundamental factors. And this can be used to ultimately improve the performance and quality of the product. Particle track and PVM provide an enhanced process understanding. Together, they enable formulators and engineers to quickly associate droplet system dynamics with process conditions while running fewer experiments than traditional methods and with no sampling required. Optimize batch-to-batch repeatability. The particle track trends and the PVM images enable formulators and engineers to troubleshoot unexpected process changes and minimize batch failures, improve yield, and troubleshoot scale-up or technology transfer. And identify batch endpoint. The particle track distributions and PVM images provide immediate, targeted endpoint detection, which ensure consistent downstream process efficiency and ultimately product quality.